Okay, so today we will discuss the result which we have stated yesterday, and which shows the existence of the Riemann integral, Riemann Stieltjes integral, and in a particular case a Riemann integral. All alpha, we have taken the class of all Riemann Stieltjes integrals. So, if f belongs to all alpha, means f is an element of the class all alpha, that is a Riemann Stieltjes integrable functions. If and only if for every f sin l greater than 0, there exists a partition, there exists a partition P, there exists a partition P such that the upper sum of the function f with respect to alpha minus the lower sum of the function f with respect to alpha over this partition is less than f sin l. So, for every f sin l greater than, there exists a partition which this condition holds. So, this condition is a if and only if condition. Let it be put it the condition as say 1. So, let us see the proof. Suppose the condition holds, suppose 1 hold, that is this for some partition for a given f sin l, we can identify a partition. So, that this result upper sum minus lower sum is less than f sin l. Okay. Now, for any partition P, we know or we have the lower sum of the function f with respect to the alpha, where alpha is a monotonic function defined over the interval a b. Okay. So, this is less than equal to the lower sum of the function, lower integral of the function f, which is less than equal to the upper integral of the upper Riemann Stieltjes integral of the function f, which is less than equal to the upper sum of the function f over alpha. This we have already discussed, because how to define the lower integral and upper integral of the lower Riemann Stieltjes integral of this is defined as the supremum value of the lower sum f with respect to the alpha, while the upper Riemann Stieltjes integral of the function f is defined as the infimum of the upper sum of f with respect to alpha. So, if I remove infimum and supremum, then this quantity will always be greater than the upper sum will always be greater than or equal to the upper integral, while lower sum will always be less than equal to the lower integral. So, for any partition P, this result holds. Okay. Now, using the condition 1, what the condition 1 says, that there exists a partition P such that the difference between the upper sum and lower sum is less than f sin. This is given. So, since this result 2 is true for any partition, so in particular this particular partition, the upper sum minus lower sum will remain less than f sin l. Therefore, using this we see here that 0 is less than equal to upper integral Riemann Stieltjes integral minus the lower Riemann Stieltjes integral, this remain less than f sin l, because this difference is less than f sin l. So, this and this is non-negative, because the upper sum and lower sum is defined the maximum value m I and delta alpha I and so on, where alpha is a monotonic function. Okay. So, we are getting for that clear. So, we get this less than f sin l, but f sin l is arbitrary number, but f sin l is an arbitrary number. So, once it is arbitrary, it can choose any for any f sin l however small, this result hold. So, this shows that lower integral and the upper integral Riemann Stieltjes integral coincide, and once they coincide, then this implies the f belongs to the class R alpha, the Riemann Stieltjes integrable functions. So, this one. Conversely, suppose f belongs to class of all Riemann stage integrable functions, then we have to show that condition 1 holds. Now, once f belongs to Riemann stage integral, it means upper sum and lower sum coincide and equal to this. So, what we get from here, the upper sum is the infimum value of this, okay, and lower sum is the infimum lower integral, upper integral is the infimum value and lower integral is the supremum value of this. So, suppose I take this f belongs to R, means that lower integral and the upper integral both coincide, first thing, okay, they are equal. Now, use this thing. If I remove the infimum, then what happens is, because this is the infimum value. So, this will remain less than this value. So, if I take a number slightly higher than this, then there will exist a partition P 2, where this value will plus epsilon will be greater than this number. Similarly, here if I remove this supremum, because this is the largest value. So, this is greater than equal to this number. So, if I take a number slightly lower than this, then there exists a partition where this number is greater than the number this minus some number epsilon by 2. So, there exists by the definition I am calling definition A, okay. Definition we can say that let epsilon greater than 0 is given. So, with this epsilon there exist partitions say P 1 and P 2 such that the upper sum of the function f with respect to alpha over the partition P 2 minus integral f d alpha is less than epsilon by 2, and lower sum of this integral f d alpha minus lower sum of f with respect to alpha over partition P 1 is less than epsilon by 2. This we can get it this. So, let it be equation say third. Now, if we take the common partition, let P is the P 1 union P 2. Okay. So, if we take the refinement of this is the refinement of P 1 and P 2. So, if this result holds for this, then for the refinement also we can get this general result. What we get is upper sum, since P is the refinement of P 1 P 2. So, upper sum decreases and lower sum increases, this we have already discussed. So, start with this upper sum of the function f with respect to alpha over the partition P, which is the refinement of P 1 P 2. Since upper sum decreases, so this is the less than equal to upper sum of the function f with respect to alpha over the partition P 2. Further, using the 3, the upper sum of this is less than integral f d alpha plus epsilon by 2, is it not? Now, using the second part of this 3, integral f d alpha is less than further lower sum of P 1 f alpha plus epsilon by 2. So, this is less than epsilon plus epsilon. Okay. So, what we get it from here, we get this, that u p f alpha minus L. Okay. One more thing is, because this lower partition lower sum increases for the refinement. So, this is further less than L p f alpha plus epsilon. So, this minus this f alpha is less than epsilon, at least this is true for this partition P. So, there exists a partition P. So, there exists a partition P for which condition 1 holds, and that proves the results. Okay. So, this now this result gives a guarantee or criteria for a function f to be Riemann stress integrable function if the upper sum minus lower sum is less than epsilon for some partition p. In particular, when alpha x equal to x, then you can get the corresponding corollary as a corollary. If alpha x is identically x, then f belongs to R, the Riemann stress integral, Riemann integral, if and only if there exists a partition P such for given epsilon greater than 0, there exists a partition P such that upper sum of the function P f minus the lower sum of the function f with respect to partition P is less than epsilon, and this is if and only part for the existence result for the Riemann integral function, integrable functions. So, this proof is okay. As a corollary we can get. Now, from this result we can derive few more conditions where we can say is sometimes sufficient condition, sometimes necessary condition for the function to be in Riemann stress integral or in particular Riemann integral. So, we have this theorem. The theorem says in the 3 parts, if one holds, if condition 1 holds, means that is there exists a part, that is for every epsilon greater than 0, there exists a partition P such that upper sum of the function f with respect to alpha minus lower sum of the function f with respect to alpha is less than epsilon. So, if this condition holds for some, this condition holds for some partition P and some epsilon, holds for some partition P and for this is 1 okay, and for some epsilon greater than 0, then the condition 1 holds with the same epsilon, for every refinement of P of the partition P. Means the condition 1 says that there exists some partition for every epsilon there exists a partition. Now, what it says is, if suppose this result hold for some partition for this epsilon, then for the same particular epsilon this result will hold for any refinement. If we take a refinement of P, say P star, then this result will continue to hold good. Okay. The proof of course, is simple. Let me see the proof. In case of let P star be the refinement of P with the same epsilon, greater than 0. This epsilon we are having the partition which is the refinement of P. Okay. Epsilon I am not changing, refinement of P, but when P star is the refinement of P, the upper sum decreases and lower sum increases. So, upper sum of this is greater than equal to the upper sum of this partition of f with respect to alpha over the partition P star, and the lower sum of this is increases, this decrease increases. So, minus of this will decrease. So, L of P star f alpha, but this is less than epsilon it is given. So, this implies that upper sum of the function f with respect to alpha over the partition p star minus the lower sum of the function f with respect to alpha over the partition p star is less than f sin r, where the p star is the refinement of H true. So, hold. So, this proves that. Second result says, if one holds, if the condition, if condition 1 holds for the partition P, say x naught, x 1, x 2, say x n, and if S I and T I is suppose are the arbitrary points in the interval x I minus 1 x I, then the sigma of this f of S I minus f of T I under modular sign multiplied by delta alpha I is less than f sin r, I is 1 to n. This is true. So, it means if this is the partition of a b interval, and if this is the point say x I minus 1, this is the point say x I, and if we picked up the 2 point S I and T I in this sub interval x I minus 1 to x I, then the functional value at the point S I minus T I, sigma of this multiplied by delta alpha I is less than f sin r. That is what it says, that if the function, if the condition 1 holds, that is if there exists for a f sin r greater than 0, if there exists a partition such that this upper sum minus lower sum is less than f sin r, then it will also imply that this condition will hold. The reason is again very simple. The proof is giving like this. What is our f of S I and itna? Since f of S I and f of T I both belongs to the interval m I into n capital M I, where what is m I and capital M I, where m I is the infimum value of the function f x when x less than greater than equal to x I minus 1 and less than equal to x I, and capital M I is the supremum value of the function f x when x lies in the interval x I minus 1 to x I. So, both these values are in the interval m I and capital M I. So, if we start with this, say upper sum and the lower sum. What is the upper sum? Upper sum is f of S I minus lower sum. So, what we get it? F of S I sigma. So, consider this thing, I is 1 to n mod of S I minus f of T I. Consider this multiplied by delta alpha I. Now, f I and S I is one of the value lying between this. So, both are lying between m I and capital M I. So, clearly f S I and minus f T I mod of this will remain less than or equal to m I minus small m I, is it not? So, we can say this is less than equal to sigma m I minus small m I is 1 to n delta alpha I, but this is nothing but what? The difference of the upper sum minus lower sum with respect to the partition P, upper sum minus lower sum of the function f with respect to alpha over the partition P. Okay. And this already given by condition 1. because condition 1 holds. So, this is true by condition 1. So, this is therefore, this sum will be less than this. So, this proves the proves. Now, third portion which he says, if suppose if f is Riemann stress is integral with respect to alpha and the hypothesis of B and the hypothesis of B, that is sigma of this thing is less than epsilon for partition P x naught x 1 x 2 and S I T I are the point in between this x I minus 1 and x I, then this condition holds, this hypothesis is given hold, this hypothesis hold, then sigma of f t I delta alpha I minus integral a to b f d alpha is less than epsilon, that is all. Okay. I is 1 to n, 1 to n. So, proof is, let me see, the proof we will start with again similar way. What? Start with the lower sum of the function f with respect to alpha over the partition P. This is equal to sigma I is 1 to n small m I delta alpha I, but m I is the infimum value of this function. So, obviously, this will remain less than equal to the value of the function f t I, where t I lies between x I minus 1 to x I. This is the point. So, I is 1 to n and then delta alpha I. But again this value is less than equal to its maximum value. So, it will be less than equal to sigma I is 1 to n m of I delta alpha I, because this is the supreme value of this function and which is nothing but what, upper sum of the function f with respect to alpha over the partition P. So, this is the one result. So, this shows that is the lower sum of f with respect to alpha this satisfy this condition, let it be 4. Okay. Further, the lower sum of this, because f is given to be Riemann integrable function. So, the supreme value of this will coincide the integral f d alpha. So, if I remove supreme, it is less than equal to this, and again the infimum value of the upper sum is this. So, this is less than equal to upper sum of f with respect to alpha. This holds for any partition P, is it not? So, if I take the 4 and 5 together, then what we get? If you take the 4 and 5, so 4 and 5 together imply this difference. If I take this difference, then what happens is the difference is coming to be 0. In fact, tending to 0 is very small, because u p alpha minus alpha is less than epsilon. The condition in the hypothesis 2, hypothesis 2 holds means the condition 1 holds. 1 holds means difference of u minus L is less than epsilon. So, difference of this minus this is less than epsilon in absolute value implies I is 1 to n, then f of t I, take this difference, okay, m I, and this I will say here, this part you can take it here, okay, and then again this is less than. So, we need this part. So, less than f of t I minus integral f d alpha modulus of this, that is sigma of this under this modulus of this is less than epsilon holds. Okay. Now, this result also suggests the way to define the Riemann integral or Riemann stress integral, because we have discussed the definition of the Riemann integral and Riemann stress integral by constructing the lower sum and the upper sum, and then finding the supremum and infimum value, and if the lower integral and upper integral coincide, then we say f is Riemann integrable function, Riemann stress integral, and when alpha x equal to x, then it is the Riemann integrable function. Now, in most of the books earlier, if you see, they do not take it to the upper sum and lower sum. What they start with a function f defined over the interval a b, okay, and then functions we assume to be a continuous function, bounded function sometimes, and then what they do is they partition the interval, find out the point in the subinterval, take the value of f of t I, and then multiply this by the delta alpha I. So, the delta alpha is left, is delta alpha I, this is left. So, multiply delta alpha I and taking the limit when n is sufficiently large. It means, when the number of the partitions are more infinity unfold. So, when the points are very close to each other, then this integral limit exists, we call it this integral of the f d alpha and existence, and we say the integral exists. So, this is the way of defining the Riemann integral or Riemann stress integral, clear. So, however, the both way equivalent way of defining, but here this is a more better way, because you are explicitly you are constructing the sum and then seeing the things, because this will go like this. If suppose I have a graph of the function, say like this, suppose this is our a, this is our b, and let us partition it. Okay. So, this will be our partition and like this. Now, when you are choosing the value, then what you are doing is you are constructing this sum in this interval, you are taking the infimum value of the function. So, this is the infimum value of the function over this interval. So, you are taking this, then infimum value in this interval, you are taking this sum, infimum value on this, and total sum you are choosing, and then changing the partition over this, and basically after this changing etcetera, we will get this limit when the supremum and infimum value coincide, then we say the integral function is integrable. And what is the upper sum? Upper sum in this case will be this much. When you take second upper integral, this is the lower integral will give, and upper sum will give this part. Okay. So, here also this is the in this interval the upper sum is this. So, we can take this one, okay, like this, and continue this one. So, when you choose the limiting value, they basically the upper sum decrease it and lower sum will increase, and they will coincide with this total area bounded by this curve. If the function is continuous, it represents the area bounded by the curve y equal to f x and the ordinate x equal to a and x equal to b with the axis of x. In case of the bounded functions, we say it is a enhancement of the definite integral, and we say call it as a Riemann integral for this. Okay. And when we take up the alpha x as a monotonic function and then choosing the values of x I and x I minus at the point with respect to alpha, then you get the Riemann stress integral. So, that is the difference between these three concepts. However, the way in which it is defined is basically gives the other definition, whatever the in terms of the upper sum, lower sum, or directly also as a limit of this sum. But since limit of this sum is difficult to compute the Riemann any integral, because the partition is more important. When you take the limit of this sum of the right hand side, because it becomes an infinite series. So, once you get the infinite series, then what happens is the sum of the infinite series will be difficult, unless you choose a proper partitioning point, and looking the proper partitioning point with respect to the function is not so easy. So, that is why we try to avoid that part, limit of the sum, to compute the Riemann stress integral or Riemann integral. We take up upper sum and lower sum and taking the infimum and supremum value. So, that is what is okay.